Okay, so welcome to lecture 9. In the last lecture, we've shown that through playing multiple iterations or multiple stages of normal form games, it is possible to force the agents to deviate from the best response of a single stage game. So essentially, this is like a stick and carrot strategy that we are using later stages. So basically the future expected utility of players to manage or maneuver their behaviors in early stages. Right. And today we're going to look at a slightly different scenario, but with the same goal. So we still want to change people's behaviors, but instead of having different stage games and finally many stage game, we are looking at repeating the same stage game, but for potentially infinite many times. The origin of the studies, starting from the 1980s by Axelrod from University of Michigan, who ran a series of game theoretical tournaments. And in those tournaments, he invited a number of other researchers to play an iterated prisoner's dilemma game. So what is that? It's essentially a multi-stage game where every stage game is the prisoner's dilemma game. Okay, and he would just ask people to come up with random strategies to play these games. For example, you could always choose to cooperate, or you could always choose to betray, or you can just randomly change between cooperation and betrayal, or you can design some more complicated strategies and make choices based on players' histories and so on, and all the players that enter into these competition, the winner between two players will be the person who obtains the highest payoff, and this has been repeated several times. In one of the tournaments, Axelrod did not tell the participants the number of rounds of the game, but instead fixed a probability of ending on any given round. So this eliminates the chance for people to play the game in expectation that the game will last for a certain fixed number of stages. And one of the very interesting observations that we can observe from the result of such tournaments is that if the player chooses to play betrayal all the time, then typically that player ended up to be among the bottom scorers in the tournament. Right. Remember, when we analyze the normal form game of Prisoner's Dilemma, mutual betrayal will be seen as a very desirable or sort of a predicted outcome because that's the only Nash equilibrium of the game. And also, if a person plays betrayal all the time, if we analyze the normal form game, it seems like it will not receive a very bad payoff, because if the opponent does not choose to betray the person, then this person who betrays the opponent will end up taking advantage of the other player. However, it is very interesting that if we have these repetition of games for an indefinite amount of stages, that if you always play betrayal, you would actually not ending up having a very high score. So there seems to be some dilemma here. And in this class, I'm going to address this dilemma. And I want to tell you that, in fact, you can enforce mutual cooperation by having these repeated stages of the same game. So formally, we can define a repeated game. Essentially, it's just a multi-stage game. But remember, in the last lecture, when I defined multi-stage game, I explicitly made it finite. So there are only finitely many stages. Of course, when I defined it, I said that you can have a multi-stage game with infinitely many stages. And in fact, if every stage is the same game, then that infinitely many stages will form what we call a repeated game. Okay. Here again, we are concentrating on the case when we have infinitely many stages. In the literature of repeated game, of course, you can have finitely many stage repeated games, but that's not what we are going to talk about in this lecture. Right. So, in order to represent this repeated game, what we need is just a set of players. We'll need a single normal form game as the stage game, because every stage is the same. And then we have a discount factor delta. Right. A repeated game can be considered as somehow an infinite multi-stage game where the players play G repeatedly for an indefinite number of iterations, and therefore we can view this discount factor delta as some sort of probability of the game go on to the next stage. So with probability 1 minus delta, after each stage the process may terminate. So in actual fact, the discounted reward that we're caring about is in fact just the expectation on the reward that the player may get according to this probability distribution. So we need to be specific of the components in the game model. This is because that we have not seen a game which requires an infinite number of iterations in the past. And while it is quite clear what a finite multi-stage game tree look like, when it comes to an infinite multi-stage game, we have to talk about what the game tree is. Inherently, the game tree would be an infinite data structure. So in this case, we can, of course, generalize finite trees to infinite trees. It has a root, and then with every internal node, there are going to be a number of children. But then the difference is here we do not have any leaf in the tree. So a game tree is just such a complete infinite tree, and it rooted at any node on level Tn, where t is greater or equal to 0. We built a copy of the game tree of the stage game G. Right, so basically, it look like just every pass of the game tree just consists of place of G for an infinite number of levels. Right, so that would be just the game tree here, and we fix a notation basically using history to describe nodes in the tree. So a history is just a finite sequence of strategy profiles in G, and each strategy profile of a stage game G specifies a path in the game tree. And when we have a number of such strategy profiles they put together, you can see that this corresponds to one fragment of an infinite path in the infinite game tree starting from the root. And we can also express this history using this letter H, and it denotes T lots of these strategy profiles, A1, A2, up to AT, and where each AI is itself a tuple of n strategies, each for one player. So we have AI1 up to AIN. And each node on level Tn will correspond to a history, right? And therefore, from now on, we can just refer to the nodes in the game tree as histories of playing the game, right? So because there's a one-to-one correspondence between nodes and history. And in fact, not nodes, but the players' information sets and histories, right? And this will allow us to redefine the notion of strategies. Instead of defining it as an extensive form game, which is a function that maps from information sets to actions. We just twist the definition a little bit, just saying that, okay, a strategy is a mapping that goes from the histories to actions of players. Right? It doesn't really change anything. It's just a convention when we talk about repeated games. So let HT denote the set of all possible histories of length T, and then we collect all of the finite length histories into a set capital H. A pure strategy will be a mapping from capital H to the set of actions that are available to the ith player. So that's the pure strategy for player I. And of course, we can look at behavioral strategies. These will be just giving probabilities to the actions as specific histories. All right. One thing that we need to redefine also is the outcomes of the game, because in the past when we have finite trees, the leaves are just naturally outcomes. But now because the trees are infinite, we do not have any leaves. So what is the eventual outcome of the tree? Well, you can think of not any particular node, but the entire history, or the entire set of histories that one extends another. So essentially this corresponds to an infinite path in the game tree that correspond to an infinite play of the game, and that determines an outcome of the game. Right. So every strategy profile, so here we're talking about pure strategy profile, generates a play in the game, and the play will determine an infinite sequence of strategy profiles, which forms a history. And it is defined in this way, where A1 is equal to the action that the first player take at the root of the tree. So epsilon is the empty history. So that's the root of the tree. And if you have any history A1, A2 up to AI, then AI plus 1 will be those actions that are specified by the strategies S1, S2 up to Sn on that history H. Right? So this will be the strategy profile AI plus 1. And iteratively, we just have an infinite sequence A1, A2 up to, arbitrary AN of strategy profiles. So that essentially, this infinite path is the outcome of the game, right? And of course, we have to determine the payoff that are associated with the outcomes. So also, instead of concrete payoff, we're looking at expected payoffs for player I given a strategy profile as I. Here also we're talking about pure strategy profiles. You can generalize everything to behavioral strategy profile, but I'm not going to that because it's slightly more complex. But so suppose we have a strategy profile as I for player I, then the expected payoff will be you take essentially just a discounted sum, but in this case an infinite sum of rewards at every stage, right? So you get at stage 1 you have Fi of A1, and then at stage 2 you discount the reward by a factor of delta, so delta times Fi of A2, and then next you have delta square of at stage 3, and so on and so forth. But this goes to infinitely many stages. So this is really important to have delta being smaller than 1, because if it's equal to 1, then the expected payoff diverge, which is something we don't want. So we want delta to be smaller than 1, and in this case we can guarantee, so assuming that the payoff in the stage games are bounded, then we can guarantee that this expected payoff will eventually converge to a fixed value. Right? And we can then define subgame perfect equilibrium in this case. Remember, before when we talk about subgame perfect equilibrium, it's only about finite extensive form games. But in the infinite case, it's almost the same, right? Strategy profile, suppose you define these pure strategy for all of the players. That is subgame perfect equilibrium if the restriction of all of these strategy profiles and natural equilibrium in every subgame. So if you look at the infinite tree, rooted at every history or rooted at every information set in that infinite game tree. If you go downwards, all the way to infinity, the downwards, you actually get a subgame. Right? So the condition of the SPE require that the strategy profile will be a Nash equilibrium in every such subgames. Right? So that's the definition of the game. So we've defined the game, we've defined strategies in the game, we've defined outcomes of the game, and then we defined expected payoffs, and then we defined subgame perfect equilibrium, which is what we assume how the player will play the game, suppose that they have sequential rationality. So let's look at a case study. In this case, we're still looking at prisoner dilemma case, but we are looking at the infinite repeated prisoner dilemma game, which we call an iterated prisoner dilemma. The game has the same payoff matrix for each of the stage game as in just normal PD that we introduced last time. And first of all, we can get some of the strategies out of the way. There are some trivial strategies which are called stationary. Well, not actually trivial, because later on they were going to play a very big part. But in this context, stationary strategies are not very interesting, because here we're assuming that regardless of what the stage is, the players will choose exactly the same actions in every stage game, right? For example, you can have this DD strategy profile. So you can have this SD being equal to S1, S2, where S1 is just D and S2 plays D. So they betray each other for all of the information set, or so for all of the history of the game. This is an SPE, as we discussed in a multi-stage game. The Nash equilibria of the stage games will actually correspond to a SPE of the multi-stage game. Right. However, if you look at another stationary strategy, which is mutual coordination, say the first player always chooses C and the second player always chooses C, so they mutually cooperate with each other. This is not an SPE, because if one player knows that the opponent will always choose C, then it's really easy for this player to exploit this fact, to take advantage of the other player by deviating from C to a D and getting higher rewards. So this is not a stabilizing configuration. Right? So this is not SPE. But how can we, in this setting, when we have infinitely many stages, is it still possible that we can enforce mutual cooperation? Right. We can imagine in this way. So even though all the stages are the same, every player has in fact two options, either to choose to cooperate or to choose to betray. And suppose that the players start off playing the mutual cooperation. It is still possible that the player would change their mind and switch to betrayal later. So in this sense, you can imagine that one of the player may use this possibility of betraying the opponent to act as a threat to the opponent, and saying, if you do not cooperate with me now, then in the future you will face consequences. But instead of facing like punishment in the form of explicit punishment, the player may say that the punishment that I will give you will be that I will betray you in the future. Right? This formally can be captured by a type of strategy which we call trigger strategy. And this particular trigger strategy is called Grim Trigger. If you look at what the players do at first stage, both players will choose to cooperate. So say just look at player 1. The player 1 strategy at the first stage will be just to cooperate. And for every other later stages, the player will still choose to cooperate if so far the history that has been developed by the players have always been mutual cooperative, right? So every earlier stage, we can see CC, right? The both players cooperating with each other. In this case, the first player would just say that, okay, I would just, because everything goes smoothly for now, I will just continue to cooperate. However, if the history is not like this, right, this means that the player betrayed one another. So one of the players betrayed another player at some earlier stage. Then this player 1 will say that, okay, from now on, I will betray you, right? So the player would choose to play the action D. And exactly the same situation happens at player 2. The player 2 adopts the same strategy, starts by cooperating with the opponent, but at every later stage, it chooses to cooperate only when so far we have only seen mutual cooperation. But otherwise, it just betrays the opponent. All right. So this is when both players are playing the Grim Trigger strategy. And I can illustrate the Grim Trigger strategy in this way, right? This is from the perspective of player 1. And in fact, for those of you who have done some elementary theory of computation course, you may have seen such diagrams, namely a finite state automata, right? So we're defining this sort of Grim Trigger strategy using a finite state machine. You can think of the strategy as consisting of only 2 states. There's a happy state, and there is the grudge state, or it's the really bad state. And you can see that in this state, this is absorbing, because regardless what the players do, the first player will respond by betrayal, right? By the action D. So I'm using this notation where we have a strategy of the opponent, and then a comma, and then a colon, and then a strategy of the first player. So this is saying that the first strategy of the second player, that's what the first player sees. So he has input as this round's, as the previous round's player 2 strategy, and then the output will be a decision on the current stage. So the action is taken by the current stage, right? So visually, you can see that this player start off this arrow, that this only incoming arrow. That is the initial decision of the player. So the player would just choose to play cooperation. And whenever he sees cooperation from the opponent, he would just say, okay, I will just stay at cooperation. But whenever there is any stage where the opponent player chooses to D, he will say, okay, I will also switch to D in the next stage. And then from now on, no matter what the opponent does, I will just stay at D, right? So I stay angry forever. And a possible play if only player 1 follows this strategy. So I'm not looking at player 2. Player 2 can be following some arbitrary strategy. So the first row here is indicating the behavior of the first player, and the second row here, that's indicating player 2's strategy. And of course, player 1 is playing in response to player 2's strategies. So initially, suppose they both play C. Of course, being consistent with the strategy, player 1 will start with C. So it has CC, 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 and then suppose at that moment player 2 for some reason switch to behavior D, to action D, then at this iteration, player 1 sees that, okay, player 2 now betrays me, and in the next iteration, player 1 immediately switch to this grudge state and say, now I'm going to betray you as well. And then player 2 stay at D, or player 2 change to C. It doesn't really affect player 1's decision. It will just stay D forever. Right? So that's a possible play of the game when player 1 follows the Grim Trigger strategy. So in this case, if you think about this strategy, so it could be that when suppose both players play the Grim Trigger strategy, it's possible that both of them will just play CC all the time. Right? Now the question is this play part of an SPE? Right? To investigate this, we recall from last lecture this important one-stage deviation principle. Of course, in the last lecture, we've only shown this for finite multi-stage game, but now we can in fact very easily extend it to infinite repeated games. So in an infinitely repeated game, a strategy profile S is an SPE if and only if there's no player I and no history H for which player I would gain from deviating from the current strategy. Right? You can see that this is one-stage deviation because we're examining only that particular history H and examining the action that available at that history. And as long as the strategy is unimprovable for any particular history, then that strategy will be a best response. And that's a criteria for us to check whether a strategy profile is an SPE. Right. By this one-stage deviation principle, we will only need to check that no player wants to deviate at any single history H, assuming the other player plays Grim Trigger. Right. So now we actually apply this one-stage deviation, and we want to decide whether CC is in fact SPE. Now we consider a history, right? Just an arbitrary history in this game. This history will be in one of the two possible states. In the first state, this is the happy state. The first state is the unhappy state. It's the grudge state, where the history is not CC. So in this case, we can, we have already seen some player betray the other player along the path of the history, right? Now we can check the expected payoff for both players, right? For any player, suppose this player would choose cooperation. What is the expected payoff? According to the specification of the Grim Trigger strategy, if we have this history, we know that both we know that both players will play betrayal infinitely many times and forever from now on, right? And therefore, we can fix that behavior of the opponent, and then we can calculate our expected payoff, supposing that we play cooperation. Right? If we play cooperation, then if you examine the payoff matrix of the game, you can see that suppose we play cooperation and the opponent will play betrayal, we will only get -1. Right? So this means that at this stage we'll get -1. Right? At this stage we'll get -1. And then we will get in a stage where if we are following the strategy, because we're only looking at one stage deviation, right? So the remaining stages are all still following the grim trigger strategy of us, and this means that in the remaining stage we still play betrayal. If you go back to the payoff matrix, you can see that when we have betrayal, we will receive 1. But this 1 will be discounted by the discount factor. So we're going to have delta, and then delta squared, delta cube, and so on. So we get an infinite sequence of delta I. We add them up to get -1 plus 1 over 1 minus delta. Right? So that's what we will get if we deviate at this current stage from D to C. Now suppose we keep doing what the grim trigger strategy asks us to do, which is to play betrayal, right? Remember, we are at this grudge state, right? So grim trigger says if you're in this grudge state, you should play D. So if you play D, you get 1 in this stage, and then you get all of the deltas also. So you get 1 plus 1 over 1 minus delta. So you can see that, of course, this value is always going to be bigger than this value. And this means that, in fact, playing D will always be better than playing C at this state. So no player would want to deviate at this history. Right. We have the second case, which is the second state. That's the happy state, when the history will be consisting of a sequence of mutual corporations. Right? And according to the grim trigger strategy, both players should play cooperation. And now let's see whether this is actually giving the players the optimal expected payoff. So at this particular history, suppose I have a player who wants to play cooperation. What is the expected payoff? It will be, so because they have mutual cooperation, if we go back to this table, we can see that the payoff will be 4 and 4. So the expected payoff would just be 4 and 4 delta and 4 delta squared and all the way on. So we add it up, we get 4 plus 4 delta over 1 minus delta. But if this player play D, so deviates from the current action of the strategy, but of course in all of the future stages he will just play according to that strategy. Right? This means that at this particular state, at this particular history, he will get 5, which is the maximum payoff he will get because he's taking advantage of the opponent. But in any future stage, he will only get 1 because both of them will, according to the strategy, will play D and D. Right? So he will get 5, and then from then on, he will get delta, delta squared, delta cube, and so on. So all the way, we get 5 plus delta over 1 minus delta. Do some calculations, we can get that delta will be greater or equal to 1 over 4 when the first value is bigger than the second value. So this means that as long as delta is greater or equal to 1 over 4, so as long as that the players will see the future utility as no less than a quarter as valuable as the current payoff, then the player would not want to deviate at this history because playing cooperation will give a higher expected payoff. Right? So when delta is greater or equal to 1 over 4, we can see that grim trigger is indeed an SPE because this is when the players, no player will want to deviate at this stage. Right? And indeed, we can see that this is a way to enforce mutual cooperation behaviors, not just for a finite number of rounds, but for forever. Right? If both players, if the players play this grim trigger strategy, and if they have sequential rationality, then playing CC all the time will actually be an SPE of the game. Right? So now we want to start to discuss a very fundamental fact about infinitely repeated games. And this is quite I would say, if you understand the reason behind it is not really surprising, but when you first see it, you think it's you think that it could be quite magical, and it's a very, very powerful theorem. No one is taking the credit for the theorem, because somehow the game theory community just collectively know about the theorem, and everybody has been talking about it, but people cannot find the first person who ever come up with it. So they just call it a folk theorem because everybody already knows it. But it's very powerful indeed. So right now what we want to ask the question of SPE of a repeated game. So if we have a repeated game, we want to know what are the SPEs. And the short answer, as indicated by the folk theorem, will be almost anything can be the SPEs. So what do I mean by this? Of course, not anything can be the SPEs, right? So what do I mean by this? Well, I mean that when we describe SPEs, typically, of course, we're describing the actions taken by the player. But suppose we do not care about the actions, but we are actually only caring about the outcome of the game. And because of the infinite play, the only thing that we care about are, in fact, the payoffs that are received by the agents, and not just the overall payoff, but rather we're interested in the average payoffs received by the players. And the short answer to the question above would then be, well, you can have an SPE that's able to generate any possible average payoff. Right. So what do I mean precisely by this? I have to fix some definition. So first of all, what do I mean by average payoff? It's defined in this way. So suppose I have a discount factor less than 1, the average payoff of an infinite sequence of payoffs P1, P2, P3. So you can imagine each of the payoffs will be the payoff for a particular stage. Then the average payoff, which I denote by putting a bar on top of this P, will be equal to, this is the definition, right? So it's defined as 1 minus delta multiplied by the discounted sum of these payoffs. Right. Why do I have these 1 minus delta term? Well, if you think about it, suppose you have an infinite sequence of payoffs of the same values, just P, say it's like 5, 5, 5, 5, 5, right? And suppose this goes on forever. Then according to our intuition about what do I mean by average payoff, I think the average payoff should be exactly that payoff, 5. Right, so if I have an infinite sequence of 5s, then the average should be 5, and this definition exactly captures this, right? Because if you add up the discounted factors of all of these p's, so you have 5 times delta square 5 times delta cube 5, and if you add everything up, you will in fact get 5 over 1 minus delta. And then if you multiply 1 minus delta, you would just review the original value 5. Right? So in this sense, this P bar indeed gives us an indication of the average payoff among an infinite sequence of payoffs. Right? So this is just a technical term, but what we want is, instead of seeking a characterization of SPEs, we would like to characterize the potential average payoffs that are achievable by SPEs of a repeated game. To formally specify the folk theorem, we need some other mathematical definitions, just to be precise about what we want to say. Suppose you get a set of vectors, and now this is a geometric term, which is a convex Hall of a finite number of vectors. You can think of the vector as points in an n-dimensional Euclidean space. Then the convex halls consist of all of the vectors that can be obtained through linear combinations of vectors in the set V. And the linear combination, if you look at the coefficient in front of every vector, so if you sum up the coefficient, that would be exactly equal to 1. Right? So this is what I mean by the convex hull of the set of vectors. Right? In fact, all of these vectors in the convex hull, it captures a space within the n-dimensional Euclidean space. Right? And all of these vectors can be obtained by some sort of combination of vectors in the set V, that's linear combination. And the weights of every term will be just add up to exactly 1. So given a normal form game, we can obtain a set of vectors. What are these? We just look at all of the outcomes of the normal form game. Remember, this is normal form games. It's a static normal form game. And we have exactly those outcomes. Suppose that S is a finite set, then there are only a finite number of outcomes. And the vector will correspond to the payoffs to every player. Right? So because we have n players, for each outcome, we will get a n-dimensional vector where we have f1s, f2s, or f1 is the payoff to player 1, f2 is the payoff to player 2, and all the way to fn, which is the payoff to player n, according to that outcome s. Right? So suppose you have all of these outcomes. With each outcome, you get a vector, you get the set of vectors. So this will be the payoff vector, as indicated by this normal form game, right? And then we can, so this is a set of vectors, we can apply the convex hull operation to look at the set of all the vectors that can be formed from the linear combination of the payoff vectors, and the weights add up to 1, right? So from all of the vectors that are in the convex hull of the payoff vectors of the game. Right, and I call these and I call these vectors the feasible payoffs of the game. As an example, if you consider Prisoner's Dilemma game, we have exactly 4 outcomes, and this means so the dimension is 2, right? So we're looking at 2-dimensional space. We have 4 outcomes, and each of the outcome will be displayed here in this grid, in this plane. We have this point, which is -1, 5. This is 1, 1. This is 5, -1, and this is 4, 4. And what are the feasible payoffs? We're looking at the convex hull of these 4 points, which are the shaded area. And so every point in the shaded area belongs to the convex hull. And then we can state the Fock theorem. Of course, Friedman first wrote it in the 1970s, but people knew it earlier than the 1970s. So suppose we have a normal form game G, and suppose we have payoffs from Nash equilibria of G, and we let P1, P2 be a feasible payoff, right? So we have these 2 vectors, U1 up to UN, which is a payoff vector that's derived from a Nash equilibrium, and then we have an arbitrary feasible payoff. And suppose now we have the case where for every player, the payoff that the player gets from this feasible payoff is strictly bigger than the payoff of this Nash equilibrium. So Pi is strictly bigger than Ui for every player I. Then for sufficiently large delta, right? So for sufficiently large delta, of course, still less than 1, the repeated game has an SPE that achieves an average payoff arbitrarily close to this feasible payoff. Right? So essentially, the Fock theorem says that if we disregard, if we make the discount factor a bit flexible, so suppose the discount factor is relatively large, as large as we can get, then essentially any feasible payoff will be sort of the outcome of some SPE as long as it satisfies this condition. This condition says that this payoff vector will be bigger than the Nash equilibrium payoff. Right. So think of this case. The only Nash equilibrium payoff vector will be 1 and 1. Right? And through the last example, we've just seen that if we look at the outcome CC, which gives us average payoff of 4, 4 to the players. And notice that 4, 4 is definitely bigger than 1, 1 in every coordinate. So for every player, this P1, P2 will now be this 4 and 4. So for every player, this 4 is bigger than the Nash equilibrium payoff of 1. So in this case, we can have an SPE whose average payoff arbitrarily close to 4, 4. So in that particular case, in fact, it's the average payoff would just be 4 and 4, right? For sufficiently large delta. Remember in the derivation, we showed that for delta greater or equal to 1 over 4, then we get that this 4 and 4 will be an outcome, an average payoff of an SPE, right? But the Folk theorem says not only we can enforce 4 and 4, but we can enforce, say, for example, 2, 2, because 2, 2 falls within the feasible payoffs. We can also have, say, 3, 3, right? Because 3, 3 is also within the feasible payoffs. So we can also have, say, 2.5, 3 or 3.5. 2.5, something like this. So anything here, we can always find a sufficiently large delta, and as long as it's both of the coordinates bigger than 1 and 1, we can have an SPE that achieves an average payoff that are extremely close, as arbitrarily close to that vector. Right, so this is very powerful because it tells us essentially anything that we think, we hope can be achieved in SPE can be achieved. How do I prove this fact? Well, I'm not going to prove it to you, but I'm going to somehow justify the theorem with you using an example, and hopefully through this example you know that why Folk theorem holds. So it's actually very, very intuitive. You like what I said. Any of the vectors that are within the feasible region and that's bigger than 1 on 1 can be the outcome of a SPE. Right. So let's just fix an arbitrary vector, say 2 and 2. Right. And now I want to define strategies in the game that forms an SPE and whose outcome will, so the expected, the average payoff that's given to the players will be arbitrarily close to 2 and 2. So how can I do that? Well, notice that, first of all, how do I form 2 and 2? I can form it by taking 0.5 of 5 and -1, and then taking 0.5 of -1 and 5, right? So this indicates that 2 and 2 is indeed a feasible payoff vector of the game, right? Because it's part of the convex hull of the game. So of the set of payoff vectors. So if the players spend half of their time playing each of the CD and CD, they will get average payoff of 2 and 2. So why do I say that? Well, because 5 and -1, this corresponds to the outcome DC, right? So actually, this one, right? This will correspond to the outcome DC, and -1, 5, this corresponds to the outcome CD, right? And because each of these outcomes has a weight of only 0.5, so this means that if the players are mixing among those infinitely many stages and mixing half of the time they play this combination and half of the time if they play this combination, then the eventual average payoff would reach 2 and 2. We'll get arbitrarily close to 2 and 2. Right? now the question is, can we enforce these actions of the players, right? And it looks like this is quite specific actions, because to enforce this, we'll need the first player to play D while the second player plays C, and we also need to enforce that the first player to play C while the second player is playing D, and we'll also need to guarantee that they alternate infinitely many times. So the proportion of time they play CD will be the same as the proportion of time they play DC. Right? It looks like a quite strong condition, but in fact, it can be very easily achieved. So I'm going to define this strategy. It's also a trigger strategy, but it's not a grim trigger strategy. So basically what player 1 does is, at all of the odd stages, at 1, 3, 5, 7, and so on, this player will play D. Right? And any of the even stages, the player 1 will play C, but only under the condition that the current history of the game is of the form DC, CD, DC, CD, and so on. So you can see that from player 1's perspective, he really wants to play this alternating DC, CD, DC, CD, but whenever anyone breaks the cycle, then player 1 would just switch to play D, right? So this C, this cooperative action, is played only when the play is going on as expected. When it's not as expected, we just not play C, but instead it will play D. Right? And similarly, exactly, player 2 is following this strategy. So this is again just a trigger strategy. So we have some expected play that we want to follow, and we just follow that play as long as the opponents are also cooperating with me to deliver that sequence of play. But as soon as we do not have this good condition that we expect, we're going to deviate from our choice, right? And this is sort of like we're giving rewards to the opponent, but as soon as we see that the opponent is not really cooperating with me, then I punish the opponent by switching to a bad action forever, right? So of course here you can see that playing C is better than playing D for the opponent. So if the first player deviates from C to D, it's essentially acting in a way to punish the opponent. So we can, just like the Grim Trigger strategy, we can visually represent this strategy using a 3-state finite state machine. We have still the scratch state, which shows that the player is unhappy, and then it's an absorbing state. No matter what the opponent does, the player would just play D all the time. But we have two other states. One is the even state and one is the odd state, because we would want the play to alternate between CD and DC. Right? So initially the player 1 will play D, and then whenever he sees a C, he will play C. Whenever he sees a D, he will play D. Remember, this C is a previous stage and this D is a previous stage. So essentially it allows the player to alternate between CD and DC, right? So this is a possible play of the game. Suppose player 1 plays, of course, player 1 starts with playing D, and suppose player 2 plays C, then the first stage will be DC. And now player 1 sees that the second player plays C, so player 1 will switch to play C and arrive at this stage, and at this state. At this state, suppose the player 2 plays D, then seeing that this fact, player 1 would play capital D and switch back to the even state. And this repeats itself as long as the second player is also following the expected sequence of actions. But for example, suppose now we are at this state even, and we see that the second player plays a D. We will only move to odd state if we see that the second player plays C at this state. But at this moment we see a D, then in the next stage we actually will move to the garage state. And then from then on we will only play D. So it will be D, 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 regardless of what the other player does. So that would be a possible play of the game. So we need to first check that once the players follow this strategy, their expected payoff will be very, very close to 2 as delta tends towards 1, so as delta become sufficiently large. First of all, we could observe that suppose the players follow these strategies, the eventual play of the game will just alternate between DC and CD. So first of all, player 1 plays D while second player plays C, and then they switch their roles. First player plays C and second player plays D, and then they iterate in this way. So we're going to produce an infinite run with this pattern. And then we can analyze the payoffs that are received by the players. So the average payoff of player 1 is 1 minus delta, multiply with the discounted total payoff, which is 5 plus delta times negative 1 plus delta squared times 5 plus delta cubed times negative 1, and so on. This is precisely because of the alternation in the outcomes of the stage games. And after some calculation, we can derive that this is equal to 5 minus delta over 1 plus delta. And you can see that the highest value of delta will be 1. So it gets closer and closer to 1. When it gets closer and closer to 1, this average payoff tends towards 2. Right. Similarly, for player 2, we can then calculate the average payoff to be 1 minus delta times negative 1 times delta times 5 plus delta squared times negative 1, and so on. And this would be equal to negative 1 plus 5 delta over 1 plus delta, which also tends towards 2 as delta increases to 1. Right. So that finishes this verification, and now we want to check that indeed this strategy profile is an SPE. According to the one-stage deviation principle, all we need to do is to ensure that no player has the intention to deviate from the strategy at any history. So we only need to look at these one-stage deviations, assuming that the player would just consistently follow the strategies afterwards. So, and also because of the players are assumed to play the same strategies, so we only need to discuss one of the players and consider a history H. According to the specification of the strategy, the history will be in one of the three states. Either it's in the garage state, or it's in an odd state, or it's in an even state. If the history is at a garage state, then we can do exactly the same analysis as the prisoner dilemma case, dilemma game, and the brim trigger strategies before, and you can actually see that player 1 doesn't really have any intention to deviate, as this will obviously lead to a worse average payoff. So what about the other two states? Suppose that the history is at odd state. According to the definition of the strategy, you can see that at any odd state, the player would want to play D. Right, and in fact, we have also analyzed in the previous slide that the player playing D would in fact get a average payoff of 5 minus delta over 1 plus delta. But what if the player deviates from that decision and choose C instead? If it chooses C, then at this moment he will be in a strategy profile of CC, because the assumed behavior of the opponent will be also to play C. So player 1 would get a payoff of 4 at that stage, but then because there's a deviation from the expected play, from now on, this player would just play D, and the other player will also play D, so they just play D, 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 D forever, and then they'll get payoff 1, 1, 1, 1, 1. So they get 4 plus delta squared, and all the way. So if we add this up, we get 1 minus delta times 4 plus delta. And notice that for any delta that are falling within the range between 0 and 1, in fact, this number would be bigger or equal to this number. So this means that player 1 will always choose D if player 1 is at an odd state. There would be no value of delta that make player 1 willing to deviate. Right? So that's showing that at least for this state, if any history fall into this state, then of course the player will not deviate. What about the other state? Say if we're in an even state, choosing C, we will get an average payoff of this, as also discussed earlier. But what about we deviate from C to D? Then the average payoff will be this much. So essentially we'll get 1 in the current stage, which is DD, and then from now on we will only get DD, so it's just 1 plus delta squared, and altogether we'll get 1 minus delta times 1 over 1 minus delta, so we get 1. Right? And notice that this value, which is the average payoff if we choose C at this stage, is bigger or equal to 1 if and only if delta is bigger or equal to 1 over 2. So now this 1 over 2 become the threshold. So whenever delta is sufficiently large, say it's larger than 1 over 2, then this player would choose to play C at the even state, and that C is consistent with the strategy, with the trigger strategy that I defined. So notice that overall we can conclude that whenever delta is above 1 over 2, that strategy will be an optimal response to the opponent, and because they are optimal response to each other, then essentially we have an SPE. Right, so the infinite repetition introduce the ability to essentially pose some reward and punishment to the opponent, where the reward would happen when the place that the players are playing so far is as designed by the player. Right, so if the player wants to achieve certain outcome, he can just say that, okay, that outcome can be realized by a mixture of strategy profiles. And the opponent has to abide by this this plan. And if so, then the opponent will get a higher payoff, and I will get a higher payoff. So that's the carrot. But whenever the opponent deviates from my plan, then I use the stick strategy. So the stick strategy will be some sort of punishment, and this will be a sort of an infinite punishment because I enter this grudge state, and I said that from now on, I'm going to inflict some pain on you forever. And then eventually the punishment will be large enough that convince the other player to not deviate from the planned actions. So this is a combination of carrot stick in very much the similar way as in the finite multi-stage game, is that we're just using exactly the same stage game but infinitely many times, right? So this is the takeaway from today's lecture. What we did was we extended the finite multi-stage game to an infinite case where we look at only those cases when the stage games are all the same, and this is called repeated game. Right? And we define this, in this scenario, the game trees and the payoffs and the outcome of such games. And then we see that, okay, the one-stage deviation principles hold for this infinitary case. And then we also showed that we can enforce still, for the prisoner dilemma case, we can still enforce mutual cooperation This is not by any external and different setup for the stage game. It's just the same prisoner dilemma game, but it's repeated infinitely many times. We can employ a strategy, namely the grim trigger strategy, to force the player to stick to cooperation. Right, and that would be an SPE of the iterated PD game. And then we discussed this very crucial and fundamental theorem, namely Fock theorem, that somehow characterizes the average payoffs that can be obtained by the players in a SPE of the repeated game. And we showed that, why it could be valid through an example. Hopefully you're convinced that essentially we can design a strategy that mix between carrot and stick to enforce the other player to comply with our plan. So that finishes today's lecture, and I'll see you in the next lecture.